So in the previous videos, you have understood how to determine the direction of magnetic force acting on a current carrying conductor using your good old Fleming's left hand. All right. So in this video, we're going to study its application, all right, and understand how to determine the direction of this magnetic field or magnetic force and how we can measure the magnetic flux density. Okay, so what I have in front of me, the diagram, is a current balance. Okay, so the current balance consists of three important devices or three important things. Number one would be a wire. Okay, so you can see that this wire is partially inside the magnet. So if you want to think about the wire, right, the wire is inside a uniform magnetic field. Okay, so this U-shape or horseshoe magnet. And let's say, just to make our lives easy, I'm just going to call this the north pole and the other side the south pole. Okay, so the magnetic field will be pointing in this direction. This is your B. All right, and also at the same time, I'm going to have to decide where's the direction of current flow. So I'm going to take the direction of current flow to, let's say, from X to Y. So this is I. So the actual complete circuit, if you are interested, or let's say, for example, this is a paper 5 question. So I'm also discussing this in case it comes out in your paper 5. So of course, current does not come from anywhere. It's going to come from a power supply. So I'll connect this to a power supply. And I would like to measure the current as well. So there has to be a switch, okay, and the ammeter connected in series to measure the current, and also a rheostat. So what the rheostat does is to change the resistance of the circuit and change the value of I. So the current will flow this way. This is your current. Okay, so oftentimes that part of the circuit is not shown in these drawings. Sometimes they show, sometimes they don't. We'll do some questions, but normally we don't show. The only thing we care about is the direction of the current. Okay, so this is the particular setup of your current balance. But what happens in this setup, and how do we determine the direction of magnetic force? So now I'm going to jump to a top view so you can see my hand and understand how the magnetic field and magnetic force act on this particular wire XY. Right, so here you can see this is a piece of paper in my hand, and I've printed out the current balance in a very big way so that we can decide how to align our hands according to a given picture on your paper. So what you see before you, I will once again label the direction of the magnetic field. Okay, so I treated a north, apologies, I treated north pole is this one, okay, and the south pole is this one. So the direction of the magnetic field will be like this. Okay, I'm going to just draw two arrows to represent this. Okay, and I'm not going to draw the complete circuit in this particular piece of paper to not overcrowd it, but I will show you the direction of current flow. All right, so the direction of current flow will be here. Hey. All right, hopefully you can see this is your I. Okay, so the direction of current flow is this way. Okay, so of course, for some people, this is a good enough diagram because what they can do is they can take out their left hand. This is F, this is B, and this is I. Okay, and then they start aligning them. Oh well, the magnetic field, which is the red line B, is pointing in this direction. Okay, so this is our B. So B is pointing in this direction. You should follow along with me if you're watching the video, or if you have the physical copy of your notes, you can do this on your screen. Okay, so B is pointing in this direction, but where is I? Right now, I is your middle finger, but the middle finger is pointing towards the camera, which is not what we want. We want the middle finger to point away from the camera or try to follow the direction of the magnet. So we will try to put this way, and then you will notice that your thumb is pointing downwards. So we can deduce that the magnetic force is pointing downwards. Focus. All right. So, but how do you know whether your direction is correct or not? Especially if, let's say, your your sense of spatial, or say your sense of space is a bit limited. Don't worry, I'm also like that. So I tend to find it easier if I actually resketch the drawing in 2D. All right, so I'm going to draw this one right now in 2 dimension. So what I will draw is I will draw a view from this angle. All right, so a view from this angle means I put my eye here. Just put my eye. Okay, and I see from here. So from the perspective of my eye, just draw some eyelash with mascara. Okay, so from the perspective of my eye, it's as if the current is going away from me. Going away. Okay, so from the perspective of the eye, the current is going away. And then what I will see is I will see this front part of the horseshoe magnet. Okay, we call this a horseshoe magnet because it looks like a horseshoe. So I'm going to draw the front part right now. And this is the front part that I will see. I'll see something that looks perhaps like this. All right, that. Okay, obviously not drawn to scale, but doesn't matter. So this is what I see. Okay, from this view, this is what I see. And from my perspective, the current is going into the paper. So I'm just going to draw a round here to represent the current or the wire XY. And the current is going into the paper. All right, your eye is here. The current is moving away from your eye. So into the paper, using your normal convention, we will use the symbol X to represent into the paper. Right? So this one will be into the paper. So it's pointing inside. Okay, so if this is X, then what will happen now is we also need to draw the direction of magnetic field. So this is the current I, represented by the symbol X, which is into the paper. Right, so I'm just going to put a note here. X means into paper. Okay, so when you're first starting, the current is into paper. When you're first starting your magnetic field studies, okay, it's always good to draw various angles and also make sure you are clear about how we represent vectors that are going out or into the paper. All right, the second thing is the magnetic field. Magnetic field will go from north to south. So since I view from this angle, north will be on the left, south will be on the right. So obviously, we follow the normal one. So this north is here, south is here. Okay, and the direction of B will be like this. This is B. Okay, so now we can use our left hand properly or a bit better because we are not confused anymore. It's pretty obvious. B will follow this direction. I is going in, so you turn your hand in. And where is your thumb now? Okay, so once again, follow along with me if you're watching the video. B is going from north to south. I is pointing inwards, going down. Where is your thumb? Thumb is pointing downwards. So if your thumb is pointing downwards, this is the direction of your magnetic force. So I'm going to pull out a different highlighter. Okay, so this is the direction of your FB, magnetic force. Okay, so you should draw this diagram beside this, especially if you have a proprioception or a spatial adjustment to make. This is a 3D diagram, this is a 2D diagram. 2D diagrams are easier for you to use your left hand, but harder for you to visualize what is happening. Okay, so let's just go through this one more time. North pole and south pole, north pole and south pole. Magnetic field will go from left to right. Ting ting. B will go from left to right, pointing left to right. Look at my middle finger. It's pointed towards the camera, which is what I don't want because current is going inside. From this perspective, current is going inside or away from the eye. So into the paper, I will rotate my hand, middle finger pointing in, thumb is going downwards, which is my F. So this finger is F. All right. So this is how we can determine the direction of FB. So this direction of FB, right, is the direction FB is the force, magnetic force on the wire. All right. So I want you to think a little bit about Newton's third law. When there is a magnetic force acting on the wire, where is the action-reaction pair? Okay. So I will see you back in OneNote where we will discuss this. Right. So as you can see, I have replicated the drawing that I have done on paper just now. Okay, just to show you the application of Fleming's left-hand rule, and we have determined that the direction of magnetic force will pull the wire downwards. Okay, so let's think a little bit about third law, Newton's third law. An action-reaction pair has to be equal in magnitude. Okay, so I'm going to just find a place to type it out. So the action-reaction pair has these four properties. Equal magnitude, opposite direction, same type of force, and acting on different bodies. So equal magnitude means both action-reaction pair has to be FB. Opposite direction meaning the force on the wire is downwards, meaning there's another force that has to act upward. What is this other force? It is also a magnetic force because they are both same type of force. Okay, and acting on different bodies. So the first body that we'll talk about, right, is the wire. Wire is being pulled by the magnet downwards. So if the magnet pull the wire downwards, the wire will pull the magnet upwards. So this FB, okay, let me zoom in first. They say opposite direction. This is the FB on the wire, and this FB will be the FB on the magnet. Makes sense? Because there are two different bodies. All right, so it's like the magnet pull the wire down, and the wire will pull the magnet up. There will be another FB here. So this FB is the force of magnet, force of wire on magnet. So one is acting on the magnet, which is this force, pulling it upwards, and the other one is acting on the wire, which is this force pulling it downwards. Okay, so now the second thing you want to think about, right, is that how would it affect the balance reading, and why on earth are we talking about a balance reading here? So the problem with measuring forces, right, is that Newton meter is not a very good force measuring device, especially the force is very small. So you should know by calculation that normally magnetic force is significantly smaller, all right? And the second problem about using a Newton meter is that it's not sensitive enough. So right now we have a more sensitive method to measure force, which is using our good friend gravity and also a top pen balance. Okay, so just to remind you, the way a balance works, okay, is that it measures the normal reaction force. Okay, so a bit of throwback to quite a lot of throwback to AS this particular video. So let's say you have an object on the balance. Let's say I put a ball on the balance. Okay, maybe a resin. So obviously there will be the weight of the resin pulling the resin downwards. So this would be mg, and there will be a contact force between the resin and the surface of the top pen balance. Okay, and this one is your reading. Because you might be thinking, but miss, how can this one be reading? So once again, a few things. This N and Mg is not an action-reaction pair. Hopefully by this point in time in your study in physics, you understand what is an action-reaction pair. This is not an action-reaction pair. These are just the forces acting on the resin. The reason why normally a physics teacher, they just quickly gloss over and tell you, oh, normal force is reading, normal force is reading. Hopefully you don't internalize it in your brain. It's reading because it's equal to Mg. No. It's equal to Mg because it's in equilibrium. All right, so this N is equal to Mg because the resin is not going anywhere. But at the same time, if I draw the forces acting on this blue color top pen balance, this will be the reaction pair, and this one is the actual reading. So these two are action-reaction pair. Okay, so this is why your top pen balance is your actual reading. All right, not because it is equal to Mg. N is equal to Mg for the first case because of equilibrium. And these two green color normal contact force is equal and is the reading of the top pen balance, right? So how much you press down is what is detected by the sensitive circuit inside the top pen balance, especially if it's digital. All right, so now let's think about this contact force or the top pen balance right now. In this case, N will be equal to Mg. So when the switch is open, This is the case when the switch is open. You have an object, N is equal to mg. So I'm just going to make a point to write here. So running out of space a bit. Okay. So when the switch is open, N is equal to mg. Okay, the reading is mg. But what happens when the switch is closed? The FB will act upwards. So when FB acts upwards, right? Let's think about your top pen balance again. You now have this normal force, which is the reading. Okay, but also at the same time, you kind of also have the magnetic force. So this is the normal force. Okay, and you also have the magnetic force pulling upwards. So if the magnetic force is pulling it upwards, you will expect the reading. What happens to the reading? Does it increase or does it decrease? You can try this experiment at home. Let's say you have a weighing balance, right? You stand on the weighing balance, okay? And then you try to push on a table. So let's say, for example, you push down on the table and you will see that the reading will decrease. Okay? Because why? There. You are pushing down on the table is pushing up on you. When the table is pushing up on you, your apparent weight decreases. You go try and see lah. Stand on a... You know what? If you want me to do this, request in the comments, I'll do it. Or let me know. So stand on the weighing balance. You press down on the table or a kitchen cabinet. Your weighing balance reading will drop. Because why? Pink color force. You press down on the cabinet. Human on cabinet. Yellow color force. Cabinet on human. So the cabinet will push the human up. So because the cabinet pushes you up, your normal contact force is less. Because the magnetic force pulls the horseshoe magnet up, the normal contact force is less. So you expect the reading to decrease. Okay, so I'm going to type out this explanation here. Of course, I guess I used to write this on the whiteboard. I think my teaching career is going to be pre and post COVID-19. So we're going to start with this. When the switch is closed, current will flow in the wire XY. Okay, and because the wire XY is in between a uniform magnetic field, using Fleming's left-hand rule, a magnetic force acts on the wire. So you think about the conditions for magnetic force to occur. Number one, there has to be current. So there's current. Okay, the wire is placed inside the magnetic field. There's a magnetic field. So because of this, there is a magnetic force. And we will use Fleming's left-hand rule to decide that the direction of current is pointing downwards. Okay, so because we use Fleming's left hand, so normally when you're asked to explain this, especially in paper 4, be very thorough because sometimes the explanation can be 4 to 5 marks. So learn to write. Start from the very beginning. We have current, we have magnetic field, so the wire will have a magnetic force. Using Fleming's left-hand rule, the direction of magnetic force on the wire, and I cannot stress this enough because you're at the level of your studies that you should know there's a difference between force acting on the wire, that means some force is pulling or pushing the wire, versus force acting by the wire, meaning the wire could push something else. All right, so from here, using Fleming's left-hand rule, the direction of magnetic force on the wire is downwards. All right, I like to call this name drop or at Fleming. I'm using your rule now. You know how you tag people, okay? So the third point here would be, because we're trying to explain what is happening to the balance reading. Okay, so to decide what happens to the balance reading, we need to decide what the balance reading measure. Balance reading will measure the contact force between the magnet and the balance, which means I need to know what are the forces acting on the magnet. All right, so from here, I can use the equation or the concept of Newton. Okay, so from Newton's third law, a reaction force acts on the U-shaped magnet or the horseshoe magnet, and the direction of this magnetic force is upwards. Hence, the balance reading will decrease. Okay, so let's say it decreases by a value of delta M. All right, because obviously we are going to measure the difference in mass. Either you take the initial and final reading and subtract, or I guess you could TARE your reading. You tare. Okay, if you don't know what tare is, means you have never baked before. So never mind, find the difference in reading. All right, so let's say this difference is delta M. All right, so we know that the cause of this change in mass, okay, here it is the magnetic field that causes the change in mass. But this change in mass reading is actually change in normal reaction force reading. So this will be delta M times G. All right. So this FB, we can use the equation BIL will be equal to change in mass times G. All right. So once again, in this experiment, the important thing here is to know what all these things are and how to measure them. Of course, delta M is the difference in balance reading before and after you turn on the current. Okay. B is the strength of the magnet, the horseshoe magnet. I is the current in the wire XY. And what about L? L would be the length of the wire. But is it the entire length XY? No, it is part of the wire that is inside of the horseshoe magnet. So it should be this. Okay, let me zoom in a bit. Ding, ding, ding. Because got feedback. Miss, your diagram too small. Okay, my bad. I can see ma. So I assume everybody can see lor. Okay, anyway, this will be your L. The portion of the wire that is inside the magnetic field. Means all the outside one, don't care. Are you saying that no matter how long I make this rod XY or wire XY, it doesn't matter? No, it doesn't matter. The rod will tell you it doesn't matter. It doesn't matter because it is only the portion that is inside the field that matters. It's like just because you register and you exist inside your college, it doesn't mean that you are. That doesn't mean that a magnetic force is exerted on you. Doesn't mean that you have a force, unless you exist within the field of the classroom and you come and learn. All right. I mean, I presume you're watching the video. You're well within the field. So we take the length of the wire that's inside the field. Okay, we're going to put it in there. All right. So I think the equation is pretty straightforward. If let's say it's a paper 4 question, you can just substitute value and see what they want. But normally the purpose of an experiment is to find the value of B. So if let's say we are going to give you a chance to do a lab, okay, I would think that a reasonable independent variable is I. So this I will be your independent variable. Okay. And what is your dependent variable? You change the current in the wire XY, you will affect the magnetic force. The stronger the pull on the magnet, by the magnet, the greater the change in mass. So this delta M, this whole thing, is your dependent variable. So dependent variable delta M. Okay, so normally what we'll do is we'll plot delta M on the y-axis. That is what is normal lah. All right, I'm going to rearrange the equation. So from here, delta M will be equal to B L over G. Is my maths correct? Yes. Multiplied by I. All right. So if you compare this with the general equation of a straight line, y is equal to mx. This one is your gradient. So what you will suggest is plot a graph of change in balance reading delta M against the current in the wire XY. How do we adjust the current in the wire XY? What will you write in paper 5? If you are thinking, nah, miss, you draw a variable resistor here. RV variable resistor. So we change the resistance. Very good. So we change the resistance, we will change the current. All right. So we will change the current. So, and then we will take the balance reading. Change the current, take the change in balance reading. Okay. The reason why I put a delta M here is to remind myself that, hey, this is a change in balance reading. All right. So what we will suggest is to plot a graph of change in balance reading against current in wire XY. Meaning we're going to have a graph that looks like this. This is delta M. Preferably kg. If not SI, then you need to convert later. It's a headache. And then this is I in ampere. So if all is good, you should get a straight line passing through the origin as such. Okay. And finally, your gradient of this graph will be equal to BL over G. Okay, so from here, you can definitely find the gradient. You know the value of G. How do we measure L? Okay, assume that this is paper 5. So the purpose, so let's say the purpose of the experiment number 1 is to determine the relationship between delta M and I. So you can determine through the shape of the graph. Number 2, determine the value of magnetic flux density B. So the way you can determine the value of magnetic flux density B is to use the gradient. So B will be equal to gradient multiplied by G 9.81 divided by the length. Okay. All right. So this value of length is the width of the horseshoe magnet, and we can measure this maybe using a vernier caliper or a meter ruler. So again, if you are doing paper 5, you make sure you mention that you measure your delta L, okay, using vernier caliper or meter rule right here for you. Measure with vernier caliper or meter rule. By the way, right, link together in this video is a video that we found where a teacher is actually running this experiment. Her method is very similar, so you can go and watch it later, but it's the same, like it's as if you do the lab, but she plot the graph for you. Yay. Okay, so from here you can actually use this current balance to determine the value. Like, let's say for example you want to measure, I wonder how strong is this magnetic field B. So you can do this experiment. You take several readings, and then based on those several readings, you can plot a graph of M against I, change in balance reading against current. And once you plot those readings, using the gradient, you can find the value of B. All right, so this is the whole idea of current balance. By placing the setup on a top pen balance, we can measure the magnitude of force, because any kind of pulling or pushing happens to the magnet will be detected as change in mass of the top pen balance. Okay, so maybe I should just write that down. The important idea. Okay, so this setup, which also is pretty helpful in your paper 5. There's another one where you want to measure electric force. Okay, so here is a hint. If you want to measure electric force, it's the same idea. The object that you are charging, let's say a metal sphere, you place it on the top pen balance. So if let's say something is pushing on the metal sphere, it will increase the top pen balance reading. Something is pulling the metal sphere up, it will decrease the top pen balance reading. So the idea of the balance reading is such that any changes in mass indicates the force on the magnet. Replace the magnet with a charged sphere, a sphere with a charge then that would be the electric force. So the change in balance reading will give you the value of F. I mean, of course, you need to take the mass multiply by gravitational acceleration, okay? Because what you have here is just change in mass, right? Okay, so in this pretty long video, we have looked at what is a current balance, how does a magnetic force that pulls the wire down gets to pull the magnet up and decrease the reading. Of course, if you change the direction of magnetic field or you change the direction of current, then the reading will increase lah. Okay, so whether the reading increase or decrease depends on this direction of FB. FB pull up, you pull something up, you hold on it and you measure the weight is less. You push something down, when you measure a weight, the weight is more. Reflected by the reading on this scale, this mg here. Alright, so we need to know how to use Fleming's left hand to decide where the direction of FB is. We also should be able to explain why the reading increase or decrease. Okay, and we should be able to design a pretty straightforward experiment. Again, don't forget to watch the experiment video that I link in the description. Okay, by writing this equation, so the reason that causes the change in mass, the change in weight, is due to the magnetic force. So you can equate this to the magnetic force and use this method to find the value of magnetic field, magnetic flux density. Alright, so there's an alternative method to find the direction of FB, the magnetic force. I will show you that in another video. If you find this explanation helpful, the current balance is actually a pretty popular recent question. We will also include some examples in later videos. But that's why, subscribe to our channel so you won't miss out any videos. Recommend us to your friend, and I hope to see you in the next one. Do take care, my friends. Bye-bye.